All set up well, John.
Why is my whiteboard not working? Oh,
It's working. You can see everything.
I can't write on it.
Really?
Oh, I don't believe.
Have you charged? How about the batteries in your pen?
Batteries in the pen. Have they gone wrong? Oh.
Because you could write only if something wrong with batteries, you may not write.
Oh, crikey, this is ridiculous.
Can you?
Not a squiggle. Let's just reload it again.
Can you try to open the Word and try to write?
We're there. Panic over, folks.
Okay.
Can you receive my squiggles?
Yes, we do.
Oh, thank goodness for that. Oh, dear. This technology is very trying. Right, what was I going to write down? Yes. Right, guys, there are 5 headings on the screen, and those are the basic headings of material I've covered in this half of the course. And within those 5 headings, there will be 4 examination questions. So what topics do you want me to talk about in the next 50 minutes? You'll have to go audio because I haven't got my chat up. I can't get in as a guest on my other machine at the moment, and I'm using full screen on my little Surface. So
I will speak up if I type on the chat.
Okay, fantastic. So topics, guys. I hope you recognize those 5 headings. If you don't, we are in difficulties.
What is the first word in number 4? Digital neural nets.
Digital neural networks. Yes, my writing is challenging for artificial intelligence. I'm not hearing anything from you, or
We're all quiet. I think we're digesting the topics.
Right. How many people have I got
17.
logged on? 17.
But this morning we had less people as well than usual.
Right, folks.
Dimitris suggests digital neural nets.
Digital neural networks. I've got a query on that. Can I have a couple of 3 more suggestions, then I'll talk about them.
Distance classifiers from Adam Wiles.
Right.
And Dimitris suggests to start.
Right. Okay. Those 2 topics we'll deal with. Let's start with the
distance classifiers comes from Stephen as well.
Okay, let's start with the distance classifiers first of all. As the word suggests, we are classifying according to distance. And the question is distance of what? It is distance between vectors. So first of all, we have to convert our data to vector form. You can do it with images by scanning the image, and every pixel intensity becomes an element of a vector. That will give you huge vectors. You can do feature extraction. You can take measurements. It could be a questionnaire when you go shopping, how much of this and that have you bought, and trying to predict the trends that you might marketing that you might buy the products again, and targeting advertising. So all sorts of things, but the key thing is the information has to be in vector form. Right, let's take a simple example, and I think I might have used this in the lectures. Let's replace the exams with a distance classifier. And supposing I'm measuring two features to get my vector, and this will be, let's call this hour study. Oops, I put 2 down there. Per week. And here is hours. What do you do in your spare time? Netflix. And so there is somebody out there who, let's call him or her person X, who spends 10 hours studying and 1 hour Netflix. So his vector or her vector will be 10, 1. And in two-dimensional space, we can actually draw it out. 3 dimensions, possible. Above 3 dimensions, we have to rely on the maths. So let's stick to the very simplest case, 2 dimensions. There is always somebody out there, person Y. And person Y is he's spending 2 hours studying and 9 hours watching Netflix. And this was data from last year. And I realized, looking at the exam records, that person X passed the exam. Person Y failed. I had to take a resit and got it a second time round. And I now want to use these 2 metrics on you guys to predict whether you are going to pass or fail the exam. So we have a pattern space. Let's go up to 10, 0 to 10, and 10 on this one. Pattern X will be point 10, 1, which will be somewhere there. The vector is the line drawing it. The point is 10, 1. So that is pattern X. And we have pattern Y, which is 2, 9. Pattern Y, somewhere down there. I'll call it Y. Why not? And that is going to be at 0.92, roughly there. So those are the 2 patterns. Now, physical distance is the distance of any points in between and their distance between the X pattern, and the X pattern was going to be pass, and the Y pattern was going to be fail. And the line of equidistance, which will be the decision surface, is actually going to be, in geometry, it is going to be, if I draw a line between the 2 patterns, this and a surface, I draw another line at right angles to it, and that line is at right angles to the midpoint between the 2 reference patterns. That is a decision surface. And the decision surface, this side of the decision surface, all the patterns are closer to X. And so that would be the pass part of the graph. All the patterns this side of the surface are closer to the fail pattern. So all we've got to do is measure physical distance. Right, let's take one of you guys, Z. Z is going to be 4, 7. 4 hours study a week, or 4 hours study a day, if you like, make it look respectable, and 7 hours watching Netflix. So let's draw the graph again. And we've got the X pattern there, which was 10, 1. we've got the Y pattern there, which was 2, 9. Those are the points of the vector. And we've now got 4, 7, which is going to be 4, 7. I guess roughly it's going to be about there. There's pattern Y. Pattern Z, sorry. Or Z if you're in America. So we have two distances. We have distance dxz, and we have distance dyz. And we have to calculate those two distances, find out which is the minimum. That will tell us which pattern, which reference pattern the unknown pattern is closest to. So in this case, looking at it, obviously, Z is closer to Y, and the pattern Z would be classed as Y, which would be a fail. Sorry, Guy, Z, you've failed, according to this. And the method we use for calculation, the accurate method, the true method, is the Euclidean distance. And the Euclidean distance is defined as d, let's say yz, is going to be equal to, let's put some dimensions on there. This is going to be, if that's pattern Z, this is going to be Z1, that is going to be Z2, and for Y, that is going to be Y2, and that's going to be Y1. We get the values off the graph, and the distance between them is this distance here, which is Z1 minus Y1. This distance here is Y2 minus Z2. And if you remember Pythagoras, the distance dy, the line there, is going to be the square root of the square of the vertical and the horizontal distance. That is basically Pythagoras. Now, in general, the order doesn't matter because we're squaring them. So for two vectors AB, DAB is going to be equal to square root of AI minus A1 minus B1, all squared, A2 minus B2 squared. And we're adding them together. Now that's for 2 dimensions. One would never use the distance classifier in 2 dimensions. It is too simple. That's not a reliable rule for passing you on the exams, for example. We might want to take 100 or 200 measurements if we were to attempt this. So for n dimensions, or d dimensions, we can extend this Euclidean formula. DAB is going to be equal to the square root of the summation over all dimensions. Here we've only got 2 dimensions. In the general case, we will have I equals 1 to D of AI minus BI squared. And that will give you the true Euclidean distance. The contour in 2-dimensional space is a circle. As we leave pattern X and move further away, the patterns of equidistance are going to be circles around X, and same for Y, and where they intersect, we will get the straight line. In 3-dimensional space, that surface becomes a plane. In multi-dimensional space, it becomes a hyperplane, whatever that is. But it doesn't matter, because although we are using a decision surface to classify the patterns, we never actually have to calculate the decision surface. To use this, we have 2 reference patterns, A and B. we simply measure the distance between an unknown and A, an unknown and B, and find the minimum distance. So that's the idea of the Euclidean classifier. The problem with the Euclidean classifier is what happens if we're using large vectors. Pictures, for example, using a pixels as the element. You could have 10 to the 6 dimensions. The vector idea still holds, but they are huge vectors. And the problem with this Euclidean surface, we have an addition for each dimension. So if there were 1 million dimensions, there would be 1 million summations. But and another 1 million additions here for the subtraction. 2's complement, remember, is how we would do the subtraction. But we've got this squaring operation, which is a multiplication, which is much longer to carry out in terms of computer instructions than addition or subtraction. So this becomes a time-consuming effort. And what we need to do is to try and cut down on the amount of time to implement this equation for large dimensions. And that leads us to approximate distances. And the approximate distances are two. One is the city block, and the second is the square. And the city block, looking at the Euclidean equation, this squaring, this multiplication operation is the problem. Let's see if we can get rid of it by saying d city block equals the summation of, instead of squaring the elements, I equals 1 to d, let's take the modulus of ai minus bi. And the modulus is simply a single addition, subtraction, and of course we ignore the sign bit. We just take the value of the subtraction, not its sign. And so we've removed the squaring operation, and that should be faster. For the square operation, it's a different equation, but it actually has the same geometrical properties as the city block. The square is a max operation of the mod. So we're looking for the biggest difference between corresponding elements to become the square distance. So those are quicker to use on multidimensional patterns, but there is a problem because the contour of equidistance is not the same as the Euclidean. And you can show this by taking a pattern. Let the pattern A be equal to 2, 2. That will do. And so I've got a pattern there, 2, 2. If I were to list patterns which were equidistant by the city block, the sum of the differences between the mods, the elements, has to add up to the distance. So if I were to take patterns a distance of 1, oh, the blaster thing. I will find out what I'm doing to make that disappear one day. It's a mystery so far. Right, distance 1, city block. I could take pattern 2, 3. I could take pattern 2, 1. I could take pattern 3, 2. And I could take pattern 1, 2. If I applied, though, the city block comparing this to this, first mod, the difference is 0. The second mod, the difference is 1. 0 plus 1 is 1. It's a distance of 1, and that would be 0.23. So that would be a point there. Similarly, for the others, 2, 1. 3, 2 would be up there, and 1, 2. So those are the points that are equidistant from 2, 2. And at that point, you might come to the conclusion that the contour could be a circle. Indeed, it could with those 4 points. And so if it was a circle, there'd be no difference from the Euclidean surface. But let's take another pattern, a less obvious pattern, distance 1. And let's try 2.5, 2.5. The difference between the first elements is 2 minus 2.5 is minus 0.5. It's the mod, so it's 0.5 plus 2 minus 2.5. Again, another 0.5. 0.5 plus 0.5 is 1. That is a distance of 1 from 0.22. And that point is, don't disappear, that point is 2.5, 2.5. That is there. Ah, why aren't you writing? That is there. And that immediately tells us the contour cannot be a circle. And if you explore this further, you can get other points there, there, and there, and you end up with a contour which is a square. Square on its side, a rhombus. And of course, the Euclidean contour is is a circle. Now, where's that disappeared to? Oh, stop it! That's the best circle I can draw. That is Euclidean. And this is a city block contour. And if we take two sets of patterns with sets of contours, we will find that with the Euclidean, circles interacting, there'll be two intersections, and that gives us the decision surface we had there, which will be a straight line. But if we intersect these rhombuses, then we'll get a decision surface which is distorted, and that can change errors. And summarizing, you need to draw it out accurately to show it, but to summarize, the decision surface for a Euclidean surface is a straight line. This would be Euclidean. And for a city block, we would get a dog, I call it a dog leg, a surface that struts the Euclidean. So this would be city block. And the key thing is, if this is the class A side and this is the class B side, if you have a pattern there, that point there, it is on the B side of the Euclidean surface. It would be classed as pattern B. But if you're using the city block, it is on the A side, and it would be classed as pattern A. So there will be some errors, some changes, some patterns which are ambiguous using the distance classifier. But if you're using this to predict social trends in shopping, or whether you're going to go on a cruise, or whether you're going to buy holidays or whatever, then the accuracy of those particular applications is very low, and the city block is as good as the Euclidean, because your accuracy would be very small on either of those predictive roles. So that's the distance classifier in a 5-minute summary. Any questions on that? Get on the audio if needs be. Of course, if you tried the square distance, the contour, let's put the square distance up on 2 dimensions. If I take that reference pattern, the city block is like that. The Euclidean is the circle. And the square distance, hence its name, is a square which looks like that. And of course, if you read up on distance classifiers, you will find there are other distances. The octagonal distance is a combination of the city block and the square. And of course, it's approximating and getting closer to the Euclidean, but it needs more processing. So if I had, let's do an example. If I said pattern X is, let's go for 5 dimensions, 5, 4, 7, 3, 2, and pattern Y is 10, 5, 1, 8, 5. And those are my reference patterns. And along comes a test pattern. And let's have Z as 9, 3, 4, 2, 4. These are just random numbers. I don't know what they're going to come out like. Distance, Euclidean. dxz is going to be the square root. Actually, we needn't bother with the square root because the square root and the square and the normal number, they will still be monotonic. If it's closer in the square root, it's closer in the unsquared number. So first of all, it is going to be xz is going to be 5 minus 9 is minus 4 squared is going to be 16 plus 4 minus 3 is 1 squared, which is 1, plus 7 minus don't. Oh, I hate this whiteboard. 7 minus 4 is 3. 3 squared is 9. 2 minus 3 is 1 squared is 1. 2 minus 4 is minus 2 squared is 4. And that is going to be root 16, 26, 31. For the Euclidean for dyz is going to be the square root of the sum. We're now doing yz. 10 minus 9 is 1, squared is 1, plus 5 minus 1 is 4, 4 squared is 16, plus 8 minus 4 is 4 squared is 16, plus 2 minus 8 is 6, 6 squared is 36, and finally 5 minus 4 is 1 squared is 1. And that is going to be equal to root 32, 34, 40, 70. So quite clearly, using the Euclidean distance, y is closer to x than z. So the conclusion you would come to would be pattern z belongs to class y. Class x, sorry. So that's the Euclidean. If we were using the, I'll just use one of the approximate distances. If I was using city block, the dxz would be the sum of the difference of the mods. It is going to be 5 minus 9 is going to be 4, plus 4 minus 3 is 1, plus 1. 7 minus 4 is 3. 3 minus 1 is 2. 2 minus 4 is 2. It is 4, 8, 10, 12. And for dyz, it's going to be 10 minus 9 is 1. Plus 5 minus 3 is 2, plus 4, was that 4 up there? Smudged it out. 4 minus 4 is 0. 8 minus 2 is 6. And 5 minus 4 is 1. And that is going to be 1, and was it 12 or 2? Lost it now. 2. 1 and 2 is 3, and 6 is 9. I think that's going to be 10. So according to the city block, we would get a different classification. So clearly that dogleg effect has occurred in this example. We've got pattern Z, which is on one side of the decision surface for Euclidean, but on the different side for the city block. So there's an example where we get a disagreement in classification. Okay, how are we doing for time? Gosh, time is flying. That's an outline on using the city block classifier. And of course, you can use as many reference patterns as you like, and you can have more examples per class. It can end up with quite a lot of processing for a large database, a large problem. But it's using distance as the strategy for classifying. But of course, there's another problem with the distance classifier. Physical distance isn't necessarily perceptual distance. When we look at something, especially if we're looking at zooms and rotations, the distance classifiers will not give what we regard as perceived distance. So interesting, but not perfect. Okay, the other topic was digital neural networks. Right. We dealt with the analog neural network first of all, and we found the problems with the analog. Well, the big problem is training. You are finding a weight vector that defines a decision surface. Decision surface is similar to the distance classifier surface. It's a partitioning plane or hyperplane between two classes. But the trouble with the analog network, you have a set of weights. When you change the weights in training, you might introduce errors from previous patterns. The digital neuron doesn't have that problem. So it's a one-pass training. And the idea is, well, it first came from, I guess, looking at a neuron. Whoops, that's silly. If there's a natural neuron with the inputs here, most medics and engineers agree that the inputs and the outputs are firing or not firing. My writing seems to have got thin, my zoom's gone to pot, I suppose, yes. Let's go out a bit. Oh, stay where you are. That's better. So, let's draw that neuron again. There is my output Z. Here are my inputs I. Again, it can be regarded as a vector.
John,
and so, yes?
You disconnected for a second, so we missed a bit of what you said.
Right, okay, let's go back.
I think it was your problem because I haven't seen any interactions.
Okay,
Oh,
well, okay, you can pick up here without losing too much information. Natural neuron, signals on the inputs and the outputs. Let's draw one. A typical signal on Z, let's have it as Z, the output, could be very complex, but what we tend to say is the neuron is firing and the neuron is not firing. So two states, basically. Never mind the complexity of the information. We can tell there's a lot of voltage activity. It's spiking at one point and it's dormant at another point. So why not call this 1, call this 0, and call this 1. So firing is 1, not firing is 0. So if I've got binary on the input and binary on the output, what is the simplest possible process that we could have to link inputs and outputs? And with binary in, binary out, the simplest thing to consider is a logic function. And the simplest logic function would be combinational. Now, that's a long way from what the detail of the natural system, but it's an interesting engineering concept. Let's run with this and see where it gets us. So the idea then becomes, if we have a pattern, and let's go to a 3-pixel pattern, which is likely to be the resolution in exams. It would be megapixels in real life. And if we have a pattern, let's say a letter T, and I use a logic function to extract information from the site, and if I have an output F, this is logic, and if I call these A, B, and C, if I wanted to recognize that particular combination of pixels, which is known as an n-tuple, come back, then from your first year digital systems, I am sure you will all tell me that F1, the logic function I need, F1 is A and B and C. And similarly for the middle row, F2 would be not A and B and not C. And for F3, the bottom row again would be not A and B and not C. Now, if I put in a different training pattern, let's put in I hope you as a human at this very low resolution would say, well, that's a T image. It's got a bit of noise on it. But, let's put it down there, sloping top. That's easier. That's a letter T that looks a bit like that at low resolution encoding. But what we've got now is a different value on the inputs to the first logic function. It is 1, 1, 0. The function was f equals a and b and c. The very simple and obvious but key thing is if I now want to include the second pattern, I have to change my function f1. It was a and b and c. If I make it a and b and c or a and b and not c, it will recognize 1, 1, 0, but it does not lose the response from 1, 1, 1. So the training is additive. Now that doesn't happen in an analog neuron. You lose information when you add new patterns. Here you don't lose the previous response to previous patterns. That's a key property of logic systems. And for the second one, F2, it was equal to not A and B and not C. It's now seeing a different set. I want to recognize both, or not A and B and C. Forget about minimization. We're just interested in the functions. And the third one would be F3 is going to be equal to originally A, not A and B and not C, or it's not going to change. Right, add a third pattern. Let's add a third pattern. I think these were the ones I used in the lectures. Let's take a T, which has a shorter vertical, humanly recognizable as a T. So that's a T like that, whereas the first one was, if you like, a perfect T. All variations in handwriting, if you like, at a very low resolution. Right, now going back to F1, A, B, C, it already recognizes it, so no change to the first function. Not A, B, not C, it already recognizes that, no change to the second function. Third function, seeing 0, 0, 0. We have to modify F3, and F3 will now become not A, B, not C, or not A and not B and not C. Right, so we've got three functions which will recognize those three training patterns. And the time taken to recognize them, it is 2 gate delays if it's a canonical form, or if you're using memories, 1 memory access to get the response. So the number of patterns, it doesn't increase the amount of processing time, unlike the distance classifier. So those are the patterns it's seen, but we can now work out some patterns it doesn't see. And this is generalization. For each of these functions to respond with a 1, i.e. to indicate it's recognized the input has occurred before, for each of those functions to recognize a 1, I have a choice of 2 entiples in the top row, 2 in the middle, and 2 in the second. And so the generalization, there will be 8 patterns the net will recognize. Now, if we now put this into a structure, there are my 3 functions. We have to combine the responses to get an overall response. The simplest way is to sum them. And then we apply a threshold, because we want a 1 no decision. Yes, it belongs to my class. No, it doesn't. So the threshold will give us a binary output, and the inputs come from the input space. 3 inputs, and the way we connect them up will change the behavior. And there are many, in real problems, many millions of ways of connecting this thing up. There's not just one fixed structure, which is, incidentally, there is just one fixed structure for the analog neuron. Everything's connected. Here we are doing subsampling, and there's millions of ways of doing it. So that was the input. This is the mapping. For programmable logic, we will use random access memories. You should understand how to do that from level 1. That's summation, and this is threshold. And what else do I know? Oh, I think in the lectures, capital N pixels and a little n entiples. Now, we worked out from first principles that 8 patterns would be recognized with this particular training set, but the general case is G, the generalization set, and we call it G and, at least one version is G and G and means we're effectively replacing this thing with a big AND gate. And that is equivalent to a threshold T equals 3 in this case, because there's maximum is 3, or in general n over little n. And the G and threshold is equal to the product series I equals 1 to 3 of Ki and what is Ki? Ki is the number of terms that are in the logic function unminimized. It's also equal to the number of bits set in the memory if you were using RAMs to implement it. Ki is the number of terms, number of entiples. And in general, this would be large n over little n. In this case, 9 over 3 gives me 3. And of course, if I look at this, there's going to be 2 terms or 2 bits set in each memory for these functions, 2, 2, 2, multiplying together. For this problem, it gives me a generalization of 8. Now, the opposite generalization is G or, beg your pardon. And G or is equivalent of replacing the summer and threshold with a big OR gate. In other words, it will respond if at least one of the functions are at 1. And it's equivalent of a threshold equal to 1. And the equation for G or, it's a tricky one, because the number of ways of getting a response out of this with an OR gate is there's an infinite number, not infinite, but a large number. The first function could be 1, the second could be 1, the third could be 1, 2 of them could be 1, all 3 could be 1. And to avoid having to work out every possible condition, there is an ingenious shortcut for G or. Don't calculate G or, calculate not G or. And not G or is the number of patterns not giving a response. So what we want from our system is a naught on F1, a naught on F2, and a naught on F3. And that is a unique combination of responses. And the probability of that happening is not G or, is the product series again, I equals 1 to n over little n, which is 3 in our simple example, 2 to the n minus ki. 2 to the n is the number of terms possible in the function. For a 3-input function, there's a possibility of 8 terms. Going back to the image, for 3-bit binary interval, there's a possibility of 8 different states, 0, 0, 0, right the way through to 1, 1, 1. And if we work it out in this example, ki's are all going to be 2. So this is going to be equal to the product series of 8 minus 2, 6 times 6 times 6. And that is equal to 36,296, I think. But that is not G or. We need G or. So G or must be equal to the universe of patterns minus not G or. And not G or is what we've already calculated. Now U, the universe of patterns, U is 2 to the n, where n is the number of pixels. And in our very simple example, n is 9 pixels. So the universe is, in our case, equal to 2 to the 9, which is 512. So G or, what we're looking for is 512 minus not G or 296. Was that correct? 36 times 6. 6 6 is a 30. 2 1. It should be 2 1s. Oh, where's the calculator? Can't do arithmetic these days.
216, John.
216. I thought that looked a bit wrong. So 216 is not G or. We want G or. 512 minus 216. And there's your 296. Which means the system generalizes and recognizes far more patterns. Now, the general behavior of that can be represented on a set diagram. And that set diagram is the universe. And that universe, remember, is big data written large. For a 9-pixel image, it is 256, which 512, which I find is quite large. If that was 16 by 16, fairly trivial resolution, your pattern universe would be 2 to the 256. And 2 to the 256 is my favorite number in the world. It's just a little bit short of the Google. It is approximately 10 to the 80. And 10 to the 80, ask Akram Khan, he'll tell you that's the number of electrons in the universe. So that universe is huge. But for our simple example, it is 512. What we have is a training set of 3 T's. Let's put them as vector points there. That is your training set for T. I'm using maybe I should call it T for the training set, T subscript T. That's the training set for T. We can get, at least before I get there to the generalization, that's the training set. There is in the world a limited set of patterns that are the letter T. In our example, for example, that pattern there by humans is not a letter T. So that's one less than infinity as the maximum size of the T set. Let's assume there is that data set. Again, a cluster in pattern space, which will be DT, the set of patterns that are the letter T. All the T's, the data set for T. And what we have now is a generalization strategy, which will create a generalization set through training on a limited set of patterns. Let's call that GT. That is the generalization set. This is the data set, and this is the training. If we can make GT equal or equivalent to DT, you have solved the problem. You have got pattern recognition. Now that is unlikely to occur in practice, but if GT is bigger than DT, it will recognize all the T's, as long as it doesn't encroach on another data set, because there'll be another data set over there, let's call that DB. As long as the generalization set of one class doesn't encroach on another set, we have got a practical system that will recognize patterns. And that is pretty smart. Okay, how am I doing for time? Gosh, I've overshot time. Sorry about that. I'll come back next week and we'll pick up on any other topics that you might want to hear more about. Okay, guys, have to finish now. Contact me by email if you have any problems.
John?
Yep.
I found, if you read now the text, I found why you are getting like sort of minimization jumping out all the time. Apparently,
Please
you
tell
tap
me.
on white space. It will double tap on white space somewhere. Yes, it will go and give you eye view.
Can I inhibit that?
Okay, so basically when you type in any space, double tap, it gives you eye view.
Yeah.
Okay, and this is what is happening.
I'll have to build a gantry over my screen so my hand doesn't touch it. Bit late now, that's the last week of lectures next week. It's caused some fun. They'll remember my lectures by my swearing.
Yeah.
They'll remember.
You have recording them as well.
Yeah. Okay. How are things, Tatiana? All right?
Yeah, it's all right. Okay, we'll catch you up with later on because I have someone on the phone with me.
Yeah, fine. Take care. Bye, everybody.
Bye.